Hello everyone, in this video presentation we're going to talk about finite state machines versus algorithmic state machines or ASM charts. Before talking about that, let's refresh quickly about finite state machine state graphs, which in the most general case could be a combination of a million more states. So for example here on the left hand side, state S0 is a more state because inside it we assign to output y1 a value. Y0 is a milli output because we assign to it a value while transitioning from one state to another. From a hardware implementation, recall that any finite state machine state graph as a combination of million more states can be implemented using three main components: the flip-flops, the memory elements that store the current state, a first combinational logic that generates the milli outputs as well as the next state, and a second combinational circuit that is responsible with generating the more outputs that depend only on the current state. So this combinational logic has as an input only the current state and generates the more outputs. The milli outputs depend on both the primary inputs as well as on the current state. An algorithmic state machine or ASM chart is just an alternative representation to the finite state machine. A finite state machine state diagram can always be converted to an algorithmic state machine chart and vice versa. So if you have one, you can generate the other one. The question would be, why would you bother to create or draw an algorithmic state machine chart at all? And the reason is that for cases, for applications, circuits that are containing this type of mixture of million more states with complex transition conditions and actions, the algorithmic state machine chart is a little bit more descriptive, and it will be desirable, better to use to write a VHDL or Verilog, if you code in Verilog, code of it. That is pretty much the main idea. So I was telling you that given a finite state machine, you can generate an algorithmic state machine chart and vice versa. You can do that by basically replacing any given state in your mixed combined million more finite state machine state graph that could look like this. Convert that to a so-called ASM block shown on the right hand side here, and the idea is really to give to the block a name that is typically the same name as the state, and then you would have here in this rectangular square box the assignment to more outputs, just like you would have inside the state, and then a possible network of boxes like this with Boolean conditions that would capture the logic of transitioning from state to another in the state graph. We'll see an example shortly. You could exit and go to other blocks, ASM blocks, directly from this conditional boxes, or after possibly assigning outputs to milli outputs. That is pretty much it. Once you have this, you can generate this and vice versa. So here is that example of a combined milli more finite state machine state graph with three states, and the transitions between states were staying within the same state as shown here. It looks, it may look simple, yet if you were to write the VHDL code of this, you would have to put some thinking, and it might be error prone. However, if you take the time and draw this somewhat, at least at the first sight, messier graphical representation, which is the ASM chart, then I'm claiming that writing the VHDL code of this would be less error prone, and you'll have a better chance to write it correctly from a first shot. And it's really easy to see how this gets converted into the ASM chart. So as I was telling you earlier, for every state, you would create a block with the same label, the same name. So we have this block S0, S1 corresponding to this state, and S2 corresponding to the state. Let's quickly look at the ASM block S0. Once you enter that, we assign directly 1 to Y1. That is the more output, and then would have a check on whether A equals 1. If that is not true, so that is the false output here, we remain within the same block or state. So when A is not equal to 1, that is A equals to 0, we are capturing this transition from state 0 to state 0 on the condition A bar. If A equals 1, so this is the output of this conditional box, we go and check for B, and if B is not equal to 1, that means B equals 0, we would exit through this output and go into block S1. So we arrive to this output out of this box through A equals 1 and B equals 0, and that is precisely this transition between state S0 and S1. On the other hand, if B was equal to 1, so we would exit out of this conditional box through this true output here. We would go on the sign to Y0, 1, that is the mealy output, and then transition to block S2. And that is, of course, this transition. A and B, when both are equal to 1, then this condition is satisfied, and we transition from this state to this state and assign 1 to the mealy output Y0. And that is exactly the path through this box as shown here. State S2 is the simplest one. We don't do anything. This is a mealy state out of which we unconditionally go back to state S0. We don't do any assignments to any mealy or more output. We just go back into the block S0. State 1, the block 1 that corresponds to state 1 is very simple as well. You enter and you assign directly unconditionally, because this is an output, a more output, 1 to Y1, and then we check on A, and if A was equal to 1, then we go back to state S0. If A is equal to 0, then we stay and come back into state S1 or block B1. So once you have this, then writing the VHDL code of that is very easy. As a reminder here, this is the hardware implementation of this sequential circuit, and if you remember when we talked about the two process coding style, that's what exactly what we are doing here. We have a first process that captures the behavior, the functionality of the memory elements, the flip-flops that store and encode the current state, and a second process in this architecture for this sequential circuit that captures the behavior of the two combinational logic circuits that generate the million and more outputs. And writing this off the ASM chart is very easy. We'll have typically a case statement with as many branches as blocks, ASM blocks in the ASM chart. So we have three, one corresponding to S0, to S1, and the third one to S2. So, for example, When we're in S0, we enter S0, we assign to this more output Y1 logic 1, and then we check on A. If A equals 1, then we continue this way and check on B, and if B equals 1, which is this path through this conditional boxes, then we assign 1 to Y0, which is a mealy output, and then we assign to state next, because S2, because the next state in which we will transition and the next clock cycle will be S2. Otherwise, state next gets assigned to S1, which captures this output of the box S0 going to S1. Now, when we're in S1, that is captured by this branch of this case statement. When S1, we enter that box and assign to Y1 1. And then we check on A1, on A, and if A is equal to 1, then we go back to state S0. Otherwise, we will stay within the same state that is captured by this first assignment here at the beginning of this process, which has some default assignments which may or may not be reassigned, changed in this sequence of sequential signal assignments within this case statement here. That is pretty much it. The simplest, the third branch of this case statement is when S2, we just assign to state next S0, meaning that we want to transition and go back the next clock cycle to S0. As you can see, three branches of the case statement each corresponding to an ASM block or box in this ASM chart. So it's very easy to just take this and write off it, the VHDL code, like so, as you can see. Imagine writing this off that finite state machine state graph that we had over here. It would be a little bit, it is doable, of course, but it is more prone to errors. That is the main takeaway. So really the main takeaway is that algorithmic state machine charts or ASM charts as an alternative representation to finite state machine state graphs or diagrams are a little bit more convenient to use when writing the VHDL code description of this applications that may contain more complex transition conditions and actions, and that is typically the case of combined million more machines. So they might be a little bit messier or may take a little bit more time to draw and create, but then writing the VHDL code of those will be less prone to errors and therefore less headaches later on trying to debug your VHDL code. So that is pretty much it. I'll see you next time.